So, hi everyone. As Cindy introduced me, I have a PhD in physics, background in physics and computer science. I'm a network scientist working as a postdoc at Social Cognitive Networks Academic Research Center at Rensselaer Polytechnic Institute. But today I'm going to speak to you about my work as a NASA data node. So as Cindy in detail introduced to you, the NASA data node is this initiative where you can work on open access datasets and collaborate with other data nodes and also with the data scientists within NASA. And we have all these cool weekly meetings where we get to see what the NASA community employees are working on, and we get to brainstorm and come up with collaboration ideas and things that we can work together on. And on top of that, we can also work on open access datasets and collaborate with each other, the NASA data nodes, and get some suggestions and ideas from data scientists and the chief knowledge architects from NASA on what is their interest and what topics they are interested in. So the OpenNASA platform, if you're going to log into the platform, you're going to see that they have made available over 32,000 data sets. And this comes as an initiative from all the other government agencies as well to make publicly available data sets and to increase visibility and transparency over government agencies. So that's why they made publicly available these data sets. And on top of that, NASA also made available some code repositories and APIs so you can access them. But this is a continuously growing platform. So if you're going to log into this platform, open.nasa.gov, you're going to be able to see the datasets, code repositories, and APIs that are currently available. And this is going to be constantly increasing, and you're going to have access to all this information. And if you're interested in this, as Cindy also mentioned, the application process is currently open, so you can apply for the spring session. And you can become a NASA data node and work on this. But even if you're not a NASA data node, you can still work on this because they are publicly available for everyone. Now, among the data sets, we also have the OpenNASA metadata, which you can find here in a JSON file format, which is going to give you basically information on all these 32,000 data sets. And if you just want to have an idea of what these data sets contain, there are some Mars rover sound data, Hubble telescope image collection, NASA patents, and picture collection from telescopes, and so on. So there are many information out there, and this is just like 5 of the 32,000. But what I'm currently interested in, and what my project here, what I'm going to talk to you about, is to understand the dataset collection. And for this, I'm going to analyze the NASA metadata, which contains information about each of these datasets, about their IDs, title, description, keyword, and all the other information that you can find. So if you're interested in this metadata, you can download it from that link. And it's going to give you a JSON format of all this information for each data set. And the question is, these data set, so each data is handled and is maintained by a different bureau within the NASA. And each bureau is going to have a person who is responsible of maintaining the NASA data online and giving it the titles and descriptions and keywords. And the question that NASA is trying to understand, to answer, is whether these descriptions overall, these 32,000 data sets, are descriptive of the content, and these human-assigned keywords, whether they are actually reflecting what is in the data itself. Because one of the big projects that they are trying to work on is to develop this search engine with which anyone can just hit in a keyword who is not working at NASA and who is not familiar with the NASA terminologies, and can retrieve meaningful data sets from this data collection. But the question is whether these human-assigned titles, descriptions, and keywords are indeed representative. And in order to do that, we have to analyze these data sets. So the questions, among others, is which of these features is best to tie together the data in order to analyze it? How do we label groupings in a meaningful manner? And we also want to see how we can visualize them and how we can obtain additional information from looking at connectivity patterns and how these terms co-occur together and so on. And of course, the main question is whether these descriptions and keywords are representative of the content. So for this reason, I'm going to use natural language processing with Python to analyze how actually these human-assigned keywords are meaningful and whether we can actually build a search engine, and based on this, we can accurately find information through the data sets, or we actually need to do some improvement. So for natural language processing, if you are not familiar with the techniques and packages, there are several packages out there. My current analysis is using NLTK, and you're going to be able to find after this presentation on GitHub, on that link, my Jupyter notebooks, and you'll be able to reproduce with that all the data that I'm going to present you here and all the results. So the first thing that we're doing when we have this tremendous amount of text, we're going to generate these word clouds to see first the frequency and to visualize the frequency of the terms within the data. So for that, we're going to build these word clouds. Of course, I used rockets and spaceships because NASA. And you're going to be able to see what are the most frequently occurring keywords. And basically what we can see is that it's dataset, Earth, ocean, aqua, spectral band. So if we look at the titles, we're again going to see similar information. But here we're going to see that the most frequently occurring words in the clouds are basically project names. And the project names are not very informative for people who are not aware of these projects. So for our analysis, I further removed this information when I did the cleaning of the data. And we also, if we look at the keywords, we can see science atmosphere, optics ocean, and all these keywords that are very nicely revealing which are the most frequently occurring. And of course, if you want to take this to next step further, you can also do Jupyter and Juno and whatever else visualization you want. And if you like this customized visualization technique, Andreas Müller has on GitHub this package, word cloud, and basically just need to get a stencil and then load your text, and you can obtain all sorts of word cloud shapes that you desire. But of course, the word clouds are nice and pretty, but they are not very meaningful for our analysis. So in order for us to do further analysis on the text, we need to do, like with any data set, cleaning and pre-processing. Now, the text pre-processing requires several steps. First of all, we need to move everything to lowercase. We need to convert all words to either lowercase or uppercase, depending on what you want, so that we can treat the data with capital D and data with lowercase as identical words. And you also want to remove special characters, code and numbers, which you can do with regular expressions, and that's how I removed all these NASA codes for project codes that are not going to be meaningful for people who are not familiar with these project names. And then, of course, you have to check for misspellings and to remove those. And then stop words, you have to, because these are the most frequently occurring words and they are meaningless, so you want to remove them from your analysis. And then, of course, you need to do lemmatization so that you break every word to a basic form. You're going to, if you have a plural of systems, you want to break it down to systems so that the machine learning tool is going to understand the algorithm that you're talking about the same tool and the same word. And then the same thing, you're going to do lemmatization if you want to break it down to the root of the word. So in this case, if you have compute, computer, and computation, you're going to bring it down to compute. This is going to be the one word. And then you're going to do tokenization. You're going to break down the text to the smallest parts, because basically this is what we're going to analyze, the words. And you're also going to have to do POS tagging, which is basically you're going to give, look at each word in the sentence and see if it's a noun, an adjective, and what's its position in the text. And then, depending on what's the dimension of your text, you're also going to have to do dimensionality reduction. Now, with Python, there are many ways to do stemming and lemmatization. Here, I just showed with NLTK some of the methods that you can use, but lemmatization is a more useful tool, in my opinion, because you're going to still have a valid word. If you remember the compute example, the compute is going to be the root of the word, but it's not going to be a valid word if you're studying it. And now that we looked at what are the basic cleaning methods, we're going to look at the term frequency, which is basically what we looked at when we did the word cloud analysis, but there actually we didn't have the numbers. So we saw that some words are bigger, which means that they occur more frequently, but we don't see how much more frequently. So therefore, we're going to do this term frequency analysis to actually plot the number of occurrence of each word, and then we can see that the top keywords, for example, you can see here, and how many times they occur on the x-axis. And the same thing can be done for the description, and the same thing can be done for the title. So just to reiterate what I was saying at the beginning, what the metadata contains. So these three information on keywords, description, and title of each dataset are human assigned by a person working within the bureau that is responsible of the data. So what we want to see is basically whether these keywords, descriptions, and titles are unified throughout each 32,000 datasets, and whether they are also descriptive of the content, whether the keywords describe what we see in the description, and whether we can retrieve information based just by searching through one or the other. And moving further, the term frequency is interesting when we look at it in a text, but since we have 32,000 datasets, we want to see what is the frequency of terms with respect to the data sets, to the number of documents. And for this, the best, a better approach is to analyze the TF-IDF, which is going to give you the term frequency versus the inverse document frequency. So you're going to get to see what is the importance of a term throughout all these data sets, not just throughout one data. So a term that is going to appear very frequently in one document, but it's going to not appear at all in any other document, is going to get a low TF-IDF value. So then, this way we can measure the importance of the words throughout the entire collection of data sets. And here we can see that the top 25 highest TF-IDF words in descriptions, and if we look at the mean on the right, you can see that it's going to change. So we can see that these are different words than what we saw in the term frequency as being the highest, but we can see the data is still in the top 25. So with this, we have a better understanding of what is going on over all the data sets and not just within one value overall. And then we can also look at the description, term frequency versus document frequency, and similarly for the words. And here, if we look at it, we can see it's very earthy. You have ocean, earth, land, biosphere. So it's everything you expected NASA to be. And we can have further understanding of what is going on. But then we want to see how the words co-occur with each other. So then we're going to build this word co-occurrence matrix. And this is going to give us the top most frequently co-occurring words. And the darker the color, the more frequently they co-occur. And what we can say is that data and product are the most frequently co-occurring terms. And here we look at the top 10, but if we are trying to zoom out, we can see at the top 20, and we can also increase it to top 50, depending on what we want. And if we zoom this out, we're going to get a more detailed analysis and a more detailed view of the patterns that are occurring in the network. But on top of that, there is something really cool that we can do using Seaborn, which has a cluster map, which also helps us to discover the structure in the heat maps. So this is not really visible, but you have to see the lines here. So basically, it's going to create a hierarchical structuring between the words that co-occur together and how frequently. And here I plotted for the top 20 word co-occurrence matrix. And if we standardize this, then we have, you can see on that side, a different hierarchical clustering, and we can reveal which words co-occur together and with what frequency. And this is really nice because it also discovers the structure in the co-occurrence matrix. It doesn't just give numbers, but it shows how they connect to each other. And getting back to our main question, what we want to understand is whether the features pulled from the text, such as the title, description, field, and other human-supplied keywords, is descriptive of the content of the data. So in order to do this, we're going to do topic modeling. So for those of you who don't know what topic modeling is, it's an efficient way to make sense of a large volume of text. We can identify topics within the text corpus, we can categorize documents into topics, and we can associate words with topics. So in this case, we're going to get all these 32,000 data sets, and we're going to see if we can identify topics within these data sets, and we can categorize them into topics. And we want to see how we can associate words with these topics. So who uses topic modeling? This is a very widely used technique, and of course, as I said, what NASA is trying to do is to build a search engine, and also there are many other companies and people out there who try to build search engines for their marketing purpose, and you can also use it for marketing purpose to reveal which topics are most interesting to a person, for example, for recommender products and so on. So there are several techniques of doing topic modeling, but the most common is the LDA method. So this basically is a Bayesian inference model that is going to associate each document with a probability distribution over the topics. And the topics are probability distributions over words. And then it's going to cluster these words into topics, or you can cluster documents into a mixture of topics. And its advantage is that it scales well with growing corpus. So it's going to be a useful technique, and we are going to analyze this. And of course, you're going to have to specify the number of topics, and you're going to do an analysis of, you can either do an exploratory analysis or a more detailed analysis of how to choose the optimal number of topics. But for my analysis, I chose 25 because that was the optimal number. And then if we look at this, I'm not going to show you all 25 to bore you to death, but I'm going to show you 4 topics, and if you can see, I'm plotted each topic with the 10 highest, most frequently occurring words in each topic. And as you can see, these words are not really informative, so we can see that there are similarities between the words that occur in the same topic, but we want to further analyze this and gain more insights. But if you are not familiar with topic modeling, you also need to look at to evaluate these topics and you have to do this with the topic coherence technique. So you want to see how the words that co-occur together, that are clustered together, what is their coherence. So you're going to use this topic coherence by calculating the UMass function, and it's going to give you a score, and based on this, you're going to be able to get which are the most coherent topics from these 25, or whichever you find that is optimal number. So if I look at the highest coherence in the NASA dataset collection, then I can see these are my 8 highest topic coherence clusters. And if I'm looking at this, it looks that I can see words that are synonyms and that are correlated, but I still want to gain more insight out of this. And what I'm going to do is, if I remember, I told you that each dataset has a keyword, has actually several keywords, so I'm connecting these keywords with the topics, and then I can actually see for each keyword what are the top 10 words that are revealed from the LDA method. And then if we look at this, we actually can see that there is a meaningful pattern, and we can get information. For example, for the budget topic, we get financial, fiscal, strategy avoidance, OFCIO, budget, report. So basically these are words that correspond to the keyword budget. And then we have astrophysics with trajectory, studio, circular, seismology, we have risk, earthquake, multi-hazard. So we can see that the keywords are basically representative of the words within the descriptions that were humanly assigned. And then if you want to do other clustering method, you can also use the k-means method to use as a different clustering method. And then you would do a silhouette analysis, which is going to give you the separation distance between the resulting clusters. And if you do if you calculate the silhouette score for the clusters that you have, you're going to basically obtain something like, I'm going to jump one, you're going to obtain something like this, which is going to be a plot of the number of clusters. And so the silhouette score is going to be plotted as the function of the number of clusters. And from this, you can actually see which is the optimal number of clusters for which you get the highest silhouette score. But you have to somewhere find the optimal number before it actually saturates, because you also don't want to go too high, but you want to stay somewhere below. So if I look, for example, at 5 clusters, I can see these words in each cluster, the top 10 most frequently occurring words, and these terms are going to be similar than the ones that I find in LDA method. But then, of course, there are other techniques that you can do, and you can look at text classification, other machine learning methods like K nearest neighbors, you can do decision trees, you can do support vector machines or naive-based probabilistic model to classify these data sets. And so these are the machine learning techniques that you can use, but as I said at the beginning, I'm also a network scientist, which means that I'm trying to look at every complex network and reveal relationships between them and look at connections between them and analyze their underlying network structure. So in this case, I was thinking that we can apply, because network scientists see networks in everything, I was thinking that we could apply a bipartite network analysis, and we can start analyzing the network of description and keywords. And we're going to say that we're connecting 2 words in a description if they appear under the same keyword. Now, inversely, you can connect 2 keywords if they share common words in the description. And this is going to give you 2 different networks that you can analyze and study structures, and you can reveal communities within these networks, and you can reveal additional information. So, since I'm running out of time, I'm going to go fast through this, but there are bipartite network projections that you can do. You can either analyze description and keywords, you can analyze the description with the title. So in this project, currently, I didn't look at the titles because since they mostly contain only project codes, those are not really informative and that don't really help us to meaningfully search throughout the data collection. So I excluded that from my analysis, but if you're interested, you can actually do that in your own time. And you can also look at title and keyword relationships. And if we're looking at networks, we can also analyze type of interactions. We can look at link direction, whether the link is directed or undirected. In this case, what I'm meaning, the social network example would be if we're looking at Facebook, it's going to be an undirected network because if you're a friend of mine, I'm a friend of yours. And if we say that there is a connection between them, that is going to mean that it's undirected because both of them are connected to each other. However, if we're looking at Twitter, for example, there's going to be a directed connection. Who is following who? So based on this link direction, you can reveal additional information. And then you can look at link weights, how strong the connections are. This basically you can, in this case, we looked at the co-occurrence matrix, how many times they co-occur together. So you can assign the strengths of the connection as the weight, how many times they co-occur. Or, for example, again, if I bring up a social network example, if you look at mobile communications networks, maybe I want to see not only if you called me, but I also want to see how many times you called me to actually reveal more information about how strong our connection is through the network. And there are other things you can do. You can look at structural network properties like the degree distributions, which is going to reveal connectivity patterns. You can see whether the nodes have connections, similar number of connections, or whether we have hubs which have significantly higher number of connections. You can look at average degrees, and you can reveal these communities and clusters and how densely they are connected. So there are many things you can look at, and then I'm just going to leave it at this because I'm running out of time. You can make all these nice visualizations, and you can do additional analysis. And you can find that, for example, in this case, I plotted the top 100 most frequent words that are occurring in the description text. And the external nodes are the ones that are the top most frequent words. And as we can see here, for example, there is already an information out there that the nodes with the highest connectivity are not all the same as the most frequently co-occurring words. So I'll leave it at this. I'll just wrap it up that the network structures are a powerful tool to capture additional information about interconnected systems. And so, yeah, one more thing. There is another thing that NASA is looking at is what are the important connections between NASA datasets and other datasets outside of NASA in the US government. And as I said, that this was an initiative of making publicly available all these government datasets so that they increase the visibility and transparency. So you can go on these websites and download the metadata for EPA, NSF, or all the other datasets that you can think of. And for this, on the bottom, you're going to see this package that I'm going to upload, and you can just pip install PyOpenGov, and it's going to load for you all these JSON files. And then using the Jupyter notebooks that I made available, you can also redo all this topic modeling and analysis that I've done. And the PyNASA is done by one of our DataNut colleagues who is here, Bruno. And basically this library is also just pip install it, and it's going to load for you the open NASA dataset. And so the takeaways are here, and thank you for your time. Stickers. So I don't work for NASA. So this is something. So this is basically an initiative. So we become NASA datanauts, but we don't get paid. We're doing our projects in our free time, and we're working on whatever we want at whatever pace we want. We have these meetings, webinars with NASA employees and NASA data scientists to brainstorm on topics that we can work together on. But this is all something that you do as a volunteer, basically. NASA doesn't have money for that, just for stickers.